Okay, so here we are, learning Calculus 2. We're going to start out with something that's kind of a physics idea. We are going to start out with motion along a line. So you have to be careful with this idea. Sometimes when people talk about linear motion, it may or may not mean that they mean motion on a line. It might mean that the velocity function is linear or something else. So you've just got to be careful of the context. So here we're going to talk about velocity on a line. So we've got some line with an orientation. Usually we draw our line and we at least visualize positives to the right, negatives to the left. Sometimes in physics, you could draw it vertically and positives up and negatives down, however you want it. We would refer to it as an oriented line. You know which direction is positive, you know which direction is negative. So then we have moments in time. So we've got time at A and time at B. And what we are going to do is form something called displacement. Displacement will be S of B minus S of A. S is going to be the position at a t-value of B minus position at a t-value of A. That'll be displacement. Displacement can be positive or it can be negative. Depends on which direction you're moving. Excuse me. If you're moving from left to right, S of B minus S of A is going to be positive. If your line is oriented so that positive is to the right, S of B minus S of A will be positive. If you're going to the left, if position at time A is here, position at time B is there, S of B minus S of A is going to be negative. So displacement can be positive or it can be negative. So that one is positive up there, that's negative. That's displacement. Terminal position minus initial position. Now we would love to have a formula, if we've got this important concept of S of B minus S of A, this concept of displacement, we would love a nifty math formula that could create that formula. Well, we're talking about movement along a line, and when something's moving, there is velocity of some sort. Could be zero at times. And what we remember from Calc 1 is that the integral of velocity is the integral of S prime, because position's derivative is velocity. Right? Position's derivative is velocity. Velocity's derivative is acceleration. Position, the rate of change of position is velocity, but then the rate of change of velocity is acceleration. Right? That's that sequence that you see in physics a lot. S, V, A. So if you start with the position and you take its derivative, you are going to get velocity. So position's derivative is velocity, and then velocity's derivative is acceleration. And then you can go backwards as well. So we kind of think of this sequence of events. Derivative brings you to velocity, derivative brings you to acceleration. If you wanted to get to V from A, you would integrate, and to get to S from V, you would integrate again. So we've got those three ideas that we can go back and forth between with integration and derivatives. And then in Calc 1, you learned the FTC, the fundamental theorem of calculus. The fundamental theorem of calculus says that take the antiderivative for S prime. Well, the antiderivative of S prime is just S. And if you integrate S prime, you get S. The integral and the derivative undo each other. And then we evaluate that antiderivative at the upper endpoint, at the lower endpoint, and take the difference. Bingo! Now we have it. So here is S of B minus S of A, right there. We're trying to come up with a math way to represent that. There it is. That is how we get to displacement. So if you integrate the velocity function, and again in your mind you're just imagining this ball ping-ponging around back and forth along the line, and somehow you know the velocity, probably empirically by measuring it. So now we have a velocity formula, velocity function. If we integrate it, plug in b and a, then we get displacement. So all we have to do to get to displacement is integrate v. That's it. As we're going through this, just stop me if you have a question. You can call me Jim. You can call me Mr. Voss. Call me Professor Voss. Does not matter. Any of those names I will respond to. Whatever you want to call me.
Will we be going into jerk or anything above? Or
No jerks.
Acceleration.
We will stop at acceleration. Jerk is the derivative of acceleration when you get into physics. But yeah, we won't. We'll take more derivatives possibly, but not in any meaningful physics way.
Okay.
Yeah. So let's remember back to Calc 1. Let's suppose that this is our curve. We're going to say that that's the velocity function. So the velocity function is positive over here, and then the velocity is 0, and then the velocity is negative. Well, back in Calc 1, you learned this idea of area. If you integrate a function that's above the x-axis, you're going to get the area beneath that curve. If you integrate a function that's below the x-axis, you get the area between the x-axis and the curve multiplied by -1. Right? So if you have a curve that's dipping below the x-axis, when you integrate that, you get a negative. And if you wanted the true area, you just took the absolute value of it. So if you integrate straight across from A to B, you will get geometrically whatever this area is minus whatever that area is. So built into the integral is this upper area minus lower area evaluation. So if you integrate straight, this function b from A to B, just integrate straight across, you will get upper area minus lower area. That is displacement. Displacement is going to be upper minus lower. If we wanted the distance traveled is always non-negative. Distance traveled has to be greater than or equal to 0. Right? So what we would do is take the absolute value of the v function, absolute value of v. That's going to pop that up to the numerator, up above the x-axis. And if we just add those two areas together, we are going to get the distance traveled. So if we were able to integrate an absolute value function, that would give us the distance traveled. Now, first off, absolute value of v has a word. It's called speed. That's what speed is, absolute value. Velocity always has a direction. Velocity can be negative, right? Depends on whether you're going in the positive direction or the negative direction. Velocity is what we call a vector. It's got both direction and magnitude. Speed is what we call a scalar, because it's just a number. It doesn't have direction associated with it. It's just a scalar. And in particular, speed is a non-negative scalar. So a scalar just means a number. Could be positive, could be negative. In this context, when that's the scalar we're referring to, that's always going to be non-negative. Speed. Now, absolute value of v is, can you integrate that? Does an absolute value function have an antiderivative? Can you find a function whose derivative gives you an absolute value? No, cannot. If you have to integrate an absolute value, you've got to go back and remember that the absolute value of a function is a piecewise defined function. So anytime we see an absolute value function, we should be thinking, oh, there's two pieces. There's a piece when the inside is positive or non-negative, and there's a piece when the inside is negative. And you do something different. Right? The absolute value of v is v if what's inside is, usually we put the greater than or equal to right there. You could put the equal to down below if you wanted to. And it's negative v if v is negative. Right? That's the definition of an absolute value. It's And does that make sense to everybody? Let's just look at a silly example. Let's just do that. Well, it's going to be equal to, let's see. So it's equal to itself if what is inside is positive. All right, that's not happening. And it's equal to, so if what's inside is negative, you have to multiply what's inside by a negative. So we're going to end up with this situation. Oh, I wrote that badly. I wrote that terribly. Let's just do it like this. This is easier if we do it like this. So the absolute value of -4, in your mind, you should be saying, okay, this is how the function works. First we look inside and we say, okay, what's inside is negative. Okay, that puts us right here. What's inside is negative. So this says take what's inside, the v, and multiply it by -1. So this is how we should be doing it. As soon as we have a known number inside here, we know whether we're on the top or the bottom branch. So if what's inside is negative, we're on the bottom branch. So we're going to take whatever's inside, which is v, so this is v, -4, but then we have to multiply it by -1. So a piecewise defined function always has two pieces. We just have to know which piece we're on. So if this was a function, so if we had that, if we have something like this, x plus 2, we know that, okay, well, that's going to be itself if x plus 2 is positive, or 0. And this is going to be minus the quantity x plus 2 if what's inside is negative. So now you could integrate, right? Because when you integrate, we know if we solve each of these for x, what is our transition point? What is the x value where things change? If we subtract 2 from both sides, so if we subtract 2 from both sides, -2 is our transition point. So if we were to graph this function, so if we graph that function, we are dealing with an absolute value function that's been shifted to the left 2 units. So the graph of that absolute value function is going to look, didn't want to straighten that out, but sort of like that. If you're over here, you're under this piece of the absolute value function. And when you transition at -2 to over here, now you're under this piece. Those pieces are different, right? This is x plus 2 right here. This one is y equals x plus 2. This one is y equals minus x minus 2. So if you were asked to integrate an absolute value function, you need to figure out, well, where's that transition point? If you were going to integrate across here, you'd have to break it apart right there. You would integrate. You'd integrate this function if you're to the left of -2. And you would integrate this function when you're to the right of -2. So if you have to integrate an absolute value function, you're actually going to end up doing 2 integrals, one for each piece. The pieces are defined by that transition point. So there is, long story long, there is no antiderivative for the absolute value of v. You have to break it into 2 separate pieces and integrate each piece with it broken apart at the transition point.
You don't have to break it apart if you're using a calculator, right?
It depends on the calculator. Some calculators you can type it right in and it will treat it properly and it will break it apart for you. But if you're doing it by hand, you definitely need to break it apart. All right, let's take a look at this one. So displacement and distance from a velocity function. So think about that first part. So we don't have the equation of this velocity function. We just have a picture of it. So what intervals is the object moving in each direction? So what intervals is the object moving in the, oh, I guess that just says the negative direction. So where is that? So we're visualizing again, unit, number line. Ball is ping-ponging around back and forth. When is it moving in the negative direction? So when is it moving left? What would be the intervals?
0 to 2 and 4 to 6.
What do y'all think of that? Agree? So when the velocity is negative, we're moving to the left. Velocity is negative when the graph of velocity is below the x or t axis. So 0 to 2 and 4 to 6. Is it correct to have parentheses? What happens at 0, 2, 4, and 6? What direction is the ball moving?
It's an inflection point, right? So it's
The velocity is, yeah, it's stopped. So at these points right here, the velocity is 0, so it's not moving left or right at those points because it's stopped. Everyone okay with that? So parentheses, because it says when is it moving in the negative direction. B, what is the displacement on interval 2 to 6? So if we look up here, interval 2 to 6 right there, it's saying what is the displacement from 2 to 6? What do you think for that? So 2 to 6 displacement is always upper area minus lower area. So that's going to be 4. So we'll do 14 minus 4. Oops, 14 minus 10, which is equal to 4. 14 minus 10 equal to 4. And then C says, what's the distance traveled from 0 to 6? So now we're going to go all the way across, 0 to 6. Let's see, 6 stops right there. 0 to 6, and we want distance traveled. What do we think that's going to be? So we're going to add all the areas. Everyone okay with that? So distance is always the sum of the areas. Displacement is upper minus lower. Part D, what is the displacement on the interval 0 to 8? So now we're going to go all the way across 0 to 8. And if we want displacement 0 to 8, we're going to do displacement is going to be upper. That's going to be negative, though, for that one's lower. So we're going to do upper minus lower, so we're going to end up with this kind of equation. Do we get negative 10? So do we know where the ball is on the number line after 8 seconds? Do we know where the ball is after 8 seconds? We have no idea. This just says that we are now 10 units to the left of where we were when t started at 0. But we never, in this problem, said where we are initially. So we don't know where we're starting. So from here, all we can say is that we're 10 units left of the initial position. That's all we can say. So we don't know. It all depends on where we start. We don't know where we start. We just know we're 10 to the left of where we started. So we don't know where on that number line we actually are. All we know is that we're relatively, we only know that relative position, 10 to the left of where we started. Okay, let's go ahead and take our 10-minute break. Take a break, stretch, smoke, do push-ups, whatever college students do these days. Man, times have changed. We will take another look at some of these concepts. This slide here is just summarizing what we saw. So we've said that displacement is going to be the definite integral of velocity from A to B. That'll be the displacement on an interval A to B. And if we integrate speed, we will get distance traveled. And again, it looks easier than it is because we know that an absolute value is a piecewise defined function, so that's going to actually be a little more complicated than it looks, but that's an easy enough definition. Now, a few minutes ago, we were talking about that example on the last slide where we ended up 10 units to the left of where we started. But we didn't know where we ended up because we didn't know where we started. Well, here's what the full picture is. So the position at time t will be whatever that starting point is. So that's got to be given to us. And if it is given to us, then we're going to add it to that displacement. So if we figure out the displacement on this interval from 0 to t, and then add it to our initial position, this will tell us our future position at time t. So what we're doing is building a function that's going to tell us where we are at time t sometime in the future.
Is there a reason why the displacement is an integration with respect to x?
Yes. I'll explain it in 1 second. Yep, that's a great question.
I was just going to ask if the 0 in this case is just like a temporary placement. It could be any initial position.
So the idea, yeah, the initial position can be anywhere on the number line. And if you integrate from 0 to t, this is going to give us just the displacement piece. And so then we add that to whatever this initial position is. Okay, now to answer, remind me your name again?
Austin.
Austin. So great question. So earlier we saw t and t, but notice that the integration limits don't have any letter in them. We never want the letter inside the integral to collide or be conflicted with a letter that's in a limit of integration. So we want those to be different. And that's because in this example, in this box right here, t is a variable. So this says, what is the position, not just at a specific number, what's s of 5, it's saying what's s of t. We want a function. So we want to be able to plug in any t value. We want to say, oh, if we want the position at time 5, at t equals 5, we would replace that t with a 5 and integrate 0 to 5. But if we just want it as a general function, so it's kind of a predictor of where we'll be at time t, then we have to change the letter in here so that it doesn't conflict with that variable. We usually refer to this letter inside an integral as a dummy variable. It's not really a variable. It's a dummy variable. So why is it a dummy variable? Well, if we integrate, let's suppose we integrate x squared on the interval 0 to 4. So then we do this. We do what we always do. We plug in the upper limit, so we get 4 times 4 is 16 times 4 more is 64 divided by 3. Is there a variable? Is there a variable in here? No. No, that letter always disappears. That's why we call it a dummy variable. It's just a placeholder. We use that variable, we do our calculus on it, we plug in our limits of integration, and it disappears. So that x inside the integrand is a dummy variable. It's not really a variable, so we can use whatever letter we want. Now, if we integrate from 0 to t, something like, let's integrate cosine of x dx. So if we have that, again, this now is going to be a function. So when you see a letter as a limit of integration, it means you have a function. Here, there's no letter in the limits of integration, so this is really just a number. This is just a really elaborate way to express the number 64/3. That's just a number. That's not a function. Okay, that's just a scalar right there. Whereas here, when we do our integration, when we do the integration here, we are going to see the integral of cosine of sine from 0 to t. Then we're doing the whole fundamental theorem of calculus thing. We plug in the upper limit, we get sine of t, and then we get sine of 0. And what's sine of 0? Sine of 0 is 0. Now you should be visualizing the unit circle, and hopefully it's crystal clear that sine is always the y coordinate, cosine is the x coordinate, come alphabetical order, c before s, x before y. So when you're visualizing the unit circle there, and we are at a position of 0, that means that we're right here. There's an angle of 0, sine of 0, we're right there. The coordinates of that point are x comma y. Well, just like x and y are positioned in alphabetical order, cosine and sine are in alphabetical order. Cosine, comma, sine. C before s, alphabetically. So sine is the y coordinate, sine is 0, so we end up with this as our final answer. And we notice that's a function, right? That's not a scalar. That's a scalar. This is a scalar. That's a function. So if you have a letter in the limit of integration, we always end up with a letter in the final answer, which means we have a function. If we have constants in the limits of integration, we always end up with a scalar. And the one thing that we do is to avoid conflict for our dummy variable, we make sure that it's different from the function variable. And if there is no function variable, then it doesn't matter what you use for your dummy variable. Use whatever letter, your favorite letter. Let's go to the next slide. So here we're given a velocity function. And it says determine when the motion is positive, when it's negative, find the displacement, find the distance traveled. So we want to know the t interval when we're going that way, the t interval when we're going that way. We want to know what's the displacement. We want to know what the distance traveled is. Okay. Well, we're going to need to graph this. What kind of curve is that? Parabola. It's a second order function, so we know it's a parabola. Is it a parabola that's going to open up, or is it going to open down? Up, leading coefficient's positive. We know a parabola is always going to have a vertex that's in between the two zeros, if there are two zeros. And we know that this has two zeros because we see that we can factor this really easily. If we factor out 3t, what are the zeros? 0 and 2. So if we set this equal to 0, this implies that t equals 0 and t equals 2 are the zeros. So we know that the vertex is at 1. Okay, so we don't have to be super crazy about this graph. You know, we just want to get a sense of what it looks like. So we've just said that the zeros are at 0 and 2. The vertex is at 1. We can plug it in and get the exact value. Plug in a 1 there, we get 3 minus 6, negative 3. We don't have to be super specific, though. All we care is what the relative position of all this stuff. We know that we need an interval from 0 to 3. So if we wanted to plug in 3 here, we can. We would get 27 minus 18. 27 minus 18 is 9. So we're going to be somewhere up here, somewhere like that. Again, we don't have to be super precise. It's all about relative position, where things are. That gives us plenty to answer the questions. So the first one said, determine when the motion is in the positive and negative directions. So part A, positive direction. What interval will we choose for the positive direction?
2 to 3.
2 to 3. So at 2, we notice that it's 0, so we definitely exclude 2. But at 3, isn't it still moving in the positive direction at 3? So what are we going to do? Not infinity. So because we're only going to look on this interval out to 3.
There's a closed bracket.
So a closed bracket, yeah. So we'll use a bracket because at 3, if we plug the 3 into here, we got a positive velocity, so it's still moving to the right at that moment. It's just that we're stopping our, we're just looking though at 3. We don't care what happens beyond 3. But at 3, the velocity is positive, so it's still moving to the right. And then how about movement to the left? That's still, I guess, part of... to the left, what is our interval? Zero to 2. Don't include them because those endpoints have a velocity of 0 at each of them. So there we go. All right, part B said, what is the displacement? Well, very cool. We have a neat formula for displacement. It's the definite integral. That cool thing that we learned from Calc 1. Now, unfortunately, there's not a standard symbol for displacement, so I'm just going to write a DISP. So displacement is going to be the integral from 0 to 3 of our function, 3. Now here, we have a limit of integration that's a constant. We don't have to worry about this conflict of letters. So we can use a t, we could use an x, does not matter. We can go ahead and just keep the t because there's no limit of integration that we have to worry about. So that right there is going to be our displacement. Definite integral from 0 to 3. So we'll do our standard Calc 1 thing, integrating a polynomial, add 1 to the exponent, divide by the new exponent. So the integral of this first term, add 1, get a 3, divide by 3, 3 divides 3. So we're going to get t cubed. Here, power is 1, add 1, get a 2, divide by 2, we get 3. Whoops. Everybody okay with that antiderivative process? Add 1 to the exponent, divide by the new exponent. Shocking that it works. That is a big deal. It's shocking. It's not what anyone would have ever guessed. So 27 minus 27. So displacement is 0. Displacement is 0. Distance traveled. So this is like driving to school and then driving home again. Your displacement is 0, but you certainly had distance traveled. You can tell by your gas tank. So part C, the distance traveled. So distance traveled, that we usually represent with a d. I'm going to write it as distance just to make sure that it's clear. Here, we have to integrate the absolute value of the velocity. We have to integrate speed to get distance traveled. So the integral of the absolute value of velocity with respect to t from 0 to 3. But again, there's no antiderivative for an absolute value function. What you have to do is break it into pieces. So we're going to break it into this piece right there from 0 to 2. If we integrate from 0 to 2, and then we're going to add the integral from 2 to 3. Now, when we do the integral from 0 to 2, we have to make it positive by putting a negative sign in front. Or, in Calc 1, you should have learned that another way to change the value by a -1 factor is to do what with your limits of integration?
Flip them.
You could flip them. Yeah, absolutely. You could just flip them. That's another technique, another way to mathematically write it down. So I'm going to write it this way, though, just because that's kind of how they do it, how they present it. So in our function is 3t squared minus 6t, 3t squared minus 6t dt. Okay, plus we're going to add the integral from 2 to 3. Same function, same integrand, I guess I should say. Any issues up to that point? So this will now be -1 times the area beneath the curve. And -1 times the area beneath the curve, this -1 is going to make it positive. Right, so this will be the area beneath the curve on the left, area beneath the curve on the right. Area, this is the area below the t-axis, right here. Area beneath the x or t-axis, area above. So everything is positive now. So we just go through the antiderivative process again. So we're going to get minus t cubed. So here we integrate, we get the minus 3t, but we distribute that -1. So we get plus 3t. And that's going to go from 0 to 2. And then we do the same thing over here. We integrate, add ones. That's what we get. Thank you. Good?
The other one needs a square root.
Oh, what the heck am I doing? I don't know how to add. Yeesh. Add 1. It's always the easy stuff. Adding 1. Okay, so plug in the upper limit, 2, so we get -8 plus 12. Plugging in 0 gives 0. And then plug in the 3 here, so we get 27. Minus 9 times 3 is 27. So I've plugged in the upper limit here. That's the upper limit. Now we have to subtract off. So this is where the mistakes often happen, is subtracting off the lower limit.
It's true.
Say again?
In minus 27 is wrong.
It is?
Yeah. Because it's different.
So 3 squared, what is 3 squared? 3 squared is 9. Times 3 is not 27?
Yeah. Come on. Continue.
Continue?
Yes, yes.
Okay, we'll continue and then we can decide if it's right or wrong. So then we have minus 12, we get that. Is there any piece of that anyone disagrees with? Yeah, Ari?
The first time you wrote -8 plus 12.
-8 plus 12. I'm confused. What's the question? Am I looking here?
Yeah.
So if we plug in 2, we get -8. Plug in 2 here, 4 times 3 is 12. Over here, we subtract off. So here is our antiderivative. We subtract off the evaluation at the lower limit. So we subtract off, 2 goes in there, makes 8, 2 goes in there, makes 12. Does anyone agree?
Wait, did you already distribute the negative?
No. Which negative? There's many negatives.
For-
Every time we do a lower limit of integration, there's a negative that has to be distributed. I have not distributed that negative yet. That's why there's parentheses.
For the first one, for the first integral to absolute value it, did you already distribute the negative?
That is right over here. So that negative is this negative. And so that negative gets distributed to here. Because this is t cubed, but then distributing the minus gives minus t cubed. This integrates to -3t squared, but then the negative distributes to make it positive. So that one has been distributed, which is what I think I was thinking about. I was thinking too much about the negative and didn't write the exponent properly. Okay, so then our final answer is whatever that all adds up to. Well, we've got some cancellations which make it easy, right? Those are going to cancel. Then we have -8. Oh, I guess nothing else cancels. So we have -8 and -8, which is -16. We have +12 and +12, which is 24. And so we get 8. So that is the distance traveled. Okay, next one, we have a velocity function that is an exponential function. Same basic idea. We need to visualize our velocity function in order to figure out where's it positive, where's it negative. Because when it's positive, the motion is to the right. When the velocity is negative, the motion is to the left. Okay, let's do a little quick sketch of this. So what kind of function is this? Exponential. Is it growing? Is it decaying? What's it doing? Decaying. Right? Because we're dealing with stuff to the right of 0. And when you plug in numbers to the right of 0, you have a negative exponent, which means it's going to be going down. Now, if we just plug in our two values, we'll get a perfect enough sketch. If we plug in t equals 0, we end up with an exponent of 0. E to the 0 is 1. 1 times 50 is 50. So we're up here at 50. If we plug in a 4, and we know it's a slide, right? Got one of those white water slides at Waterworld? Going down. So it's going down like that. It's not going to touch the x-axis or the t-axis, though, because this is never 0. Right? That is never 0. Its limit is 0, but it's never 0. So let's pick 4 here. We'll just say that's 4. And when we plug in the 4, we're going to get some number. We don't care what that number is right this second, but it's going to be above the t-axis. That's far enough, but that's probably way too far above, but just to make sure that it's clear that it does not touch the t-axis. All we need is the relative position of everything. So there we go. So when is this object moving to the right or in the positive direction? The whole time. Totally agree. The whole time. When you plug into 0, you have a positive velocity. When you plug in any number between 0 and 4, you also have a positive velocity. And at 4, you have a positive velocity. So yes, the whole time. When is it moving in the negative direction or to the left? Never. So never is it moving to the left, so not applicable. B, what is the displacement? Oh, we have a formula for displacement. The displacement is the integral from 0 to 4 of the function, the velocity function, 50e to the negative 2t dt. We got a formula for that. That's great. So, given that, what is the antiderivative for that function, 50e to the negative 2t? We need to be able to take the integral of this, find the antiderivative, whatever your terminology is. There is a technique, the most important technique that you learned in Calculus 1. You learned it in the last 2 weeks of the semester, most likely. It's called integration by, begins with an S. Close.
Substitution.
Substitution. Substitution. Most important technique. And we are going to come up with a very clever way to do integration by substitution without substitution. We are going to come up with a very clever way to do that in most cases. Let me point out one fact here. Is this exponent linear, quadratic, cubic? How would you classify that function? Linear, right? That's a linear function. The highest power is 1. That's linear. And we are going to see a clever way to do integration by substitution without substitution when you have a linear exponent. But first, let's do it by substitution. When you are doing substitution, you're looking at usually to set u equal to the exponent, or maybe a denominator, or what's inside of a square root. You're looking for things to let u equal. It's usually something like that. So I'm going to let u equal negative 2t, and then I'm going to take the derivative and get that differential equation. Is there any issue with the red? That allows us then to do the substitution. So this integral will now be 50e to the u. So drop the 50e to the u. Now the dt has to be replaced. To replace the dt, we look at this equation right here, and we isolate dt. When you isolate dt, you see that du over negative 2 is dt. So we're going to replace this with du over negative 2. And then for our limits of integration, we also have to do a little bit of changing. This equation right here exchanges t's for u's. If you plug in a t, you get a u. Right? It relates t with u. Up here, this says when t is 0 and when t is 4. Well, this integral down here is with respect to u, so these limits of integration must be u limits of integration. So if we plug t equals 0 in right here, we see that the corresponding u value is 0. If we take the t value of 4 and plug it in right here, we see that the corresponding u value is negative 8. Right? So we use that equation, our substitution step. That allows us to go back and forth between the two variables. So now, this is what I'm going to write next. Tell me if you agree with it. So we take this negative 2. I'm going to divide it in. I'm going to get negative 25. I'm going to factor it out to the front. This is 0 to negative 8. And then just e to the u to u. Do you agree with that? And then we know the antiderivative for e to the u is e to the u. It's the coolest function of them all. It is its own derivative. It is its own integral. We love that. It's the magic function. And then we have to do our evaluation, our FTC, from 0 to negative 8. If we don't like the fact that we're going from 0 to negative 8, that this number up here is smaller than this number down here, you could just switch it and take out the minus sign too, right? We could say, oh, let's have that limit of integration evaluation go from smaller to larger. That's usually how we're thinking, right? Smaller down below, larger above. You could do that. You could just swap them and then change the sign out. Right? If you switch the limits of integration, you multiply by minus 1. Okay, so let's evaluate. So this is going to be 25 times e to the 0. E to the 0 is 1. So now we subtract. And then we have e to the negative 8. So there is our answer. So that is what we were looking for. So this, all that work was to get the displacement, antiderivative on the interval. That's it. That's displacement. Now, using substitution, it's not hard, but there's a lot of steps there. Now, let's do substitution without substitution. All right. Let's do it. Substitution without substitution. So let's go back to right here. That was 0 to 4. Negative 2t, 3t. So that's where we were at. Let's go back in the time machine for a moment. Let's suppose that someone said, hey, what's the derivative of this function? What is the derivative there? Can someone tell us the derivative of that function? So the derivative of an exponential is itself. We always write that, if we're integrating or differentiating an exponential function, first thing is itself. So this is going to be itself multiplied by what? And what is that process called?
Chain.
Chain rule. Chain rule. So differentiate an exponential, you write down itself, and then you multiply by the derivative of the exponent, and this right here is the derivative. Key step, though, is right there. That's called the chain rule. When you have an integral that lends itself to substitution, if this is linear, you do not need to go through all this funny business. If you are doing substitution with a linear substitution instead of chain rule, we are going to do something that we're going to call the reverse chain rule. If the chain rule gives the answer with multiplication, what do you think the reverse chain rule does? Division, which we see right there. Right? Isn't -2 the same number that we used over here for chain rule? But the only difference is that we divided by -2. So here's what we do using reverse chain rule. Not only do you need to be able to integrate, you need to be able to integrate efficiently. If you were to use the chain rule for every single time you came up with a linear substitution, you would be wasting hours of your life. You could be doing more interesting math. So here's what we do. The integral of an exponential is itself divided by -2. That's it. If it's linear, that's the process, reverse chain rule. I will refer to it a lot as RCR, reverse chain rule. Reverse chain rule. We plug in the 4, and we get e to the -8. We subtract e to the 0, which is 1, and we are done. And if we took the minus sign and distributed it across, yeah, we'd get the exact same answer. 2 steps. Way faster. Whenever we have a linear substitution, that's what you want to be doing. You want to be doing RCR, reverse chain rule. Much faster, much more efficient, much more elegant. You don't want to spend your time on busy work. All right, next page. We've got work to do here.
Did we not do C?
Did we not do C yet? All of that just for part B? Oh, jeez. That's painful. Oh, there's a shortcut, right? What's part C?
Total distance.
Sometimes total distance is the same as displacement if the velocity is always positive. If the ball never goes in the other direction, if the ball never goes negative, if it's always just going in the positive direction, I guess this is positive. If it's always going in the positive direction, displacement and distance traveled are the same. If you drive one way to school, your distance and displacement are the same. Okay, so this is B and C. All right, phew. Hopefully we get some more good luck like that. Okay, so determine position function using the antiderivative method. Determine the position function using the FTC. So they want us to do 2 different techniques to finding the position function. Position function. So our position predictor. So first off, let's do it using I'm going to do the second one second and the first one first, just because. So the antiderivative method. In Calc 1, you learned that the antiderivative always has a plus c if it's not a definite integral. So if you're doing an indefinite integral, you get a plus c. So this is the antiderivative method. So antiderivative method, what we're going to do is say that s of t is equal to the integral of sine of t, and we're going to keep it indefinite. No limits of integration. So we're doing that first. So when we do this, we are going to get the integral of sine is negative cosine, but then you get a plus c. So that is your s of t. Okay, so we're basically going to sort of build s of t one step at a time. So first we get this general look for s of t. And now we need to figure out what that c is. So now we are going to use this data. It says s of 0 is 1. So I'm going to plug in a 1 for s of 0. And I'm plugging in a 0 for t. So if I plug in a 0 on the left, it's s of 0, which is 1. And if we plug a 0 in on the right, we have cosine of 0. And what's cosine of 0? 1. So we end up with 1 equals 1 with a negative in front of it, plus c. So what does c have to equal? 2. So therefore, our velocity our position function is negative cosine of t plus 2. So there is the position function using the antiderivative method. So there we found an antiderivative. Now we're going to do it with, so this is antiderivative method. So now we're going to do it with the FTC method. This is the preferred technique. But I don't care which one you use as long as you can do both. This, though, is the preferred technique. Because it generalizes more easily to other scenarios. So that is the formula that we talked about earlier. This gives us the displacement, and we add the displacement to the initial position. So let's see what we get. So we're told the initial position is 1. We're told that the velocity is sine of t, but notice I need to switch from t to x. We don't want conflict between our dummy variable and the variable that is the independent variable for the function. Right? T is the independent variable for the function. This whole side is a function of t, so we use a different letter for the dummy variable there. Now we integrate. Now here we're doing a fundamental theorem of calculus because we have a definite integral. So we have a negative cosine of x, and then that whole antiderivative right there is evaluated from 0 to t. So first, I'm going to keep the brackets here just to keep it separate from the 1. The 1 is not part of the antiderivative. This 1 is outside. All right, so we just took the antiderivative of sine, got minus cosine. So now we're going to plug in the t. So we get minus cosine of t. Minus a minus is plus cosine of 0. Cosine of 0, yeah, that's 1. So we end up with the same exact function. So same function. So either technique is fine. The fundamental theorem technique is cool because it's just sort of one direction. You just go from start to finish. The antiderivative method, you've got a little of this back and forth. You get a c, then you go plug back in and solve the c, and then you plug the c back in, so it's a little bit more roundabout. Both work. This one, I highly recommend focusing more on this one. It illustrates the concept better, that the future position is the starting position plus any change in position. And that idea gets generalized to, finance and populations and all sorts of things. This technique works, but it's not nearly as conceptually based. This is the better concept-based technique. So let's do this second one using that technique. So again, the question says, well, what is the future position? So s at time t, we think of t as some time in the future. We want to figure out the location of our ball that's bouncing back and forth. Where is it going to be? So that's going to be, well, wherever it starts, plus any change in position. So plus the change in position from 0 to t of 3 sine. Again, be careful. We don't want our variable, our dummy variable, to conflict with our independent variable, the variable of the function. So we always switch the dummy variable to x. And then we're good to go. Then we substitute. S of 0 is 1. Ooh, look. The inside of that sign has what kind of function? Linear, quadratic, cubic? Linear. Bells should be ringing. When we have a linear substitution, the normal approach in Calc 1 would be, let's do this substitution. U equals 3x, or pi x. Divide by pi. Substitute back in. Change your limits of integrate. Do all that business. We now know from above, if you have a linear substitution, all you do is divide by the derivative of that substitution. So let's do it. So first, the function part of it. Sine. Sine is the function. Antiderivative for sine, negative cosine. So let's make that a negative. So we're going to have negative, and the 3 comes along for the ride. It's just a multiplier. So negative 3, we have cosine of the exact same angle. Angle's not changing. Angle's the same. If we were doing chain rule, if we were doing a derivative, we would multiply by pi, but we are doing a reverse chain rule, so we divide by pi. So we're going to take that and divide by pi. And then that goes from 0 to t. And just to be clear, this part right here is the antiderivative part. The t and the 0 have nothing to do with this 1 over here. Right? That 1 is not part of the antiderivative. And maybe it's more helpful to do this kind of thing and block this off. If that's easier for you, then you can do it. So it's just that part that's the antiderivative. You don't end up with 1 plus whatever this is at t minus 1 plus whatever this is at 0. Because then the 1s will cancel. Right, so that 1 is outside. So we've got the 1. Now we take our antiderivative, and we're going to plug in the t. So we're going to get minus, I'm going to put the constants together, so minus 3 over pi, cosine of pi times t. We've got that. Now we subtract off antiderivative at the lower limit of integration. Subtracting off a negative is going to make a positive. This whole antiderivative right here. So positive 3 divided by pi times cosine of 0 times pi, which is 0. And what is cosine of 0? 1. So we can simplify this a little bit. I'm going to move the constants all to group them together, so I'll move them all to the front. And there's nothing we can do with this pi times t. That just stays as is. So there is our position function at time t. Any questions on that? All right, so again, when this is linear, we'll use reverse chain rule. So because that's linear, so linear implies RCR, reverse chain rule. All we do is divide instead of multiply. Super fast. Way better than substitution. So, let's just change our perspective for a minute. If we are, what we've been doing is discovering S from V, right? We've integrated V to get to S. We can also discover V from A. So you integrate A, acceleration, to get to V. So this process is parallel. If we want to find V from A, we are going to find the initial velocity and then add any change in velocity. So we found position by starting position plus displacement, which is change in position. We don't have a fancy word here for change in velocity. We just call it change in velocity. I mean, you could call it, I guess, displaced velocity or something. But we think about this as initial velocity plus change in velocity. All right. Now, you can also go into other fields, and like instead of thinking about these as mathematical functions that are physics-based, you can think of this as from other fields of math, other fields in science. If you just think of Q as a quantity, and then Q prime is its rate of change, you could do this whole exact thing and just replace the V's with Q's and Q prime, because remember, A is V prime, right? A is V prime. The derivative of velocity gives you acceleration. So this just generalizes the idea of a future value. So if you go into any sort of econ classes, you'll see this equation a lot.
Will you be using the velocity to acceleration more, or the Q value?
Velocity and acceleration more. Yeah, in here we'll do more of the physics-y type of applications, but this we'll do like a couple examples of that. Yeah. So let's go ahead. So let's do a double one. So we're starting with acceleration, and here we want to get to position. So we're going to climb through velocity to get to position. So first, okay, well, velocity from acceleration, velocity as a function of time, so our future velocity, our velocity at some time in the future, is going to be whatever the initial velocity was, plus the change in velocity. Change in velocity is the integral of velocity's derivative. Oh, that's acceleration. And we're going to change it to an x, because we're putting a 0 and a t there. So that's how we get to velocity from acceleration. All right, so this is going to be v of 0. V of 0 is 50. And then we're going to integrate from 0 to t. The acceleration function, gravity with feet and seconds, negative 32. And we're going to use an x, not a t. T's already been used. So then we're going to have 50 minus 32x from 0 to t. And this will give us, so once again, I want to point something out here that's super easy to overlook. The highlighted part here, that's the antiderivative. The t and the 0, that's what they're getting substituted into. The 50 is not part of the antiderivative. The 50 has to stay out in front. Alright, so plugging in t, we're going to get minus 32 times t. And if you plug in 0, we get 0. So now we have our velocity function. So that is our velocity function. Right there. Bless you. Now to get to position from velocity, same thing. We'll do what we did before. So position will be starting position plus displacement. Displacement is the integral of velocity. So same idea. Starting position plus change in position. Starting position is the origin, it's 0. So we're going to end up with this as our integral. So now we have our velocity function right there. 50 minus 32t. Oops, let's use an x. Let's use an x. So we've got that. So we'll do some integration here. The integral of 50 is going to be 50x minus 16x squared from 0 to t. Plugging in 0 gives nada. So we're going to end up, if we write this in descending order, that's usually how we like our polynomials written. We'll end up with that. What do we think? Any piece of that you want an explanation for? Ask now or Thursday. All right, let's do one more of these starting with acceleration. So we're from acceleration, we're going to build up to velocity and then up to position from velocity. So our concept is that to get to velocity, we're going to need to know the initial velocity plus any change in the velocity. So the change in the velocity is the integral from 0 to t of the derivative of velocity. The derivative of velocity is acceleration. So that is our formula. Plug in v of 0. Plug in the acceleration function. Ooh la la. Bells and whistles are going off. Negative. We have a linear exponent. Linear exponent, RCR, reverse chain rule. Don't have to go through substitution. We can do substitution without substituting. That is super important. So the integral of an exponential is itself, it's the magic function. It is its own derivative and integral. So we start out with itself. What's the derivative of that exponent? -1. If it was a chain rule, you'd multiply by the -1, but it's a reverse chain rule, so you divide by -1, which actually would be the same in this particular case. So we get that. And then our limit of integration, limits of integration, 0 and t. So now let's make sure we don't screw this up. So right here, this is our antiderivative, right? That's what the t and the 0 are getting plugged into. So first, let's plug in the t. Plugging in that t, we are going to get negative e to the negative t. And what happens when we plug in 0? What do we get? So if we plug in x equals 0, e to the 0 is 1. This whole thing doesn't become 0, right? E to the 0 is 1. So in here we have a negative 1. Right? If you were to plug that 0 in right here, you end up with negative 1. But because it's the lower limit of integration, we're subtracting. So we're subtracting negative 1. So we end up with plus 1. So that will be the velocity function. That velocity function looks like that. There's our velocity function. Let's put a box around you. So velocity function will then lead us to the position function. The position in the future, S of t, that means future position, will be starting position plus any change in position. The change in position is the integral of the position's derivative. Right? S prime is the rate at which the position is changing. But S prime is velocity. So we integrate the velocity from 0 to t to get that change in position. So initial position was given to be 40. The velocity we just found, that's going to be 61 minus e to the minus x dx. And we change the letter to x so that we don't have any conflict between the dummy variable and the function variable. The function variable is the t. So when we integrate the 61, we end up with 61x. Once again, we are integrating an exponential that has a linear exponent. To integrate with a linear exponent, all we do is take the derivative of the exponent and divide by it. So we're good to go. So 61x, we get minus integral of an exponential is itself divided by the derivative of the exponent. Evaluate 0 to t. So we'll have 40. And now this is the antiderivative, all this. Right, that 40 is out in front. The t and the 0 are getting plugged into just that green box. So first, let's plug in the t. So we're going to get 61t plus e to the negative t. And to make sure we don't make a mistake, we're going to subtract off the green box evaluated at 0. So we're subtracting off the antiderivative at 0. So subtracting off inside the parentheses is whatever that is. So 0 plus e to the 0, 1. So then our final answer, that's going to be a negative 1, so we end up with 39 plus 61t plus e to the minus t. That is our position at time t. That was our ultimate goal, finding position at time t. Ah, day 1 of Calc 2 done. For me, not for you. Any last minute questions? All right, so I'll see you all on Thursday. I'll stick around for a few minutes, but again, I can't stay all the way till 5 today because I'm heading off to a concert. But if you have questions before, then stick around. I'm going to just save the notes, and I will be free in a moment. Good to see you all. Welcome back to college.